Now I want to switch over to transient flow. We're not going to spend as much time in the theory of transient flow. I really put the emphasis on the boundary-dominated flow. Again, the reason being is because we normally assume that production data is going to be dominated by boundaries over time. Okay, long-term production data analysis is really a depletion or boundary-dominated flow problem. So this concept of generating these equations is very useful and important for production data analysis, because this is really what the wells, what wells production is going to be doing over a long period of time. The transient flow has importance over a short period of time. And that short period of time may actually turn out to be longer than we think, especially when we start to look at tight and unconventional gas. Again, because the permeability is so low. So let's investigate transient flow. It can be an important part as well. What we're going to look at here for transient flow is just a picture of the reservoir, and we're looking at it in cross-section and plan view above and below. And the red circle and the red drawdown curve here at the top indicate the pressure pulse moving into the reservoir, how far that pulse is seen into the reservoir. So this is a little bit like throwing a rock into a pond and seeing the ripples move out from the point of entry of the rock. That's the way a pressure transient moves through a reservoir. It's going to move out in concentric circles. Now, that will be true provided that the reservoir is homogeneous and isotropic. Okay, if the reservoir has properties, heterogeneous properties, or has strong anisotropy, then the shapes of these circles may be skewed. Okay, and indeed in real reservoirs that's going to be the case. So this is really an idealization of what goes on in the real reservoir. But it's a good representation. Again, when we talk about transient production, the information that comes back to the well based on this analysis is permeability, skin, and it's going to be a function of time, so things are changing with time. That's why it's called transient. Once we get into boundary-dominated flow, again, we talked about boundary-dominated flow in detail. What is the main number that comes out of boundary-dominated flow? Well, we saw we could get productivity index, and we could get the oil in place or gas in place. Okay, so it's really a volume analysis. The productivity index is a secondary thing that we can get out of it as well. If you remember from the flowing material balance, the volume was the slope of the line. The productivity index came from the y-intercept. Okay, another thing of interest here is the radius of investigation. This one can be critical in transient cases. And the reason being is this one will actually tell us how far we've seen into the reservoir. So we know that in transient production, there's a finite distance that we've observed into the reservoir, and we haven't seen beyond it. And we may want to capture how far that is. One of the reasons you may want to know that is because I've been producing my well, and I know the permeability, and I want to see what my drainage area is going to be. Or I want to be able to predict how long it's going to take to reach a certain drainage area. Okay, those are important practical questions to answer. So the radius of investigation concept will help us get a handle on that. So what I want to sort of draw your attention to here is this equation, and it's a fairly simple equation. Really the only variables that are in here are time and this combination of permeability, porosity, viscosity, and compressibility. And this conglomeration of variables is called the hydraulic diffusivity. So hydraulic diffusivity is equal to permeability divided by phi mu c. Okay. This is the only parameter that matters when talking about the radius of investigation and when talking about the pressure transient. And if you think about it, everything that's in here is an in situ reservoir property, right? It's got nothing to do with how I operate the well or the size of the well or the length of the well or whether it's horizontal or vertical well, whether it's fractured or unfractured. The only thing that matters in here is what's actually in the reservoir. So permeability is a function of the rock property itself, as is porosity. Viscosity and compressibility are functions of the fluid that sit inside the reservoir. So the hydraulic diffusivity is really an in situ property. And that's what's going to control the radius of investigation. So if we look at this and have some number for a given reservoir that represents its hydraulic diffusivity, this is going to control how quickly my radius of investigation is going to advance with time. So let's take a look at a couple of examples. The most obvious one is permeability. A tight reservoir has a low permeability. A conventional regular permeability reservoir will have a higher permeability. And the hydraulic diffusivity will be lower for a tight reservoir. Therefore, it's going to take much longer for the radius of investigation to move out into the reservoir. So if we're looking at, for example, taking a well and draining a section, 640 acres. Okay? If the permeability is very low, if it's below 0.1 millidarcies, it may take several years to drain that section. Okay? If the permeability is high, it may take only weeks or even less to drain that section or to reach the boundaries of that section. So permeability has a huge bearing on how I'm going to set up my well spacing. Okay? The denominator on here also has a big impact, mostly in terms of this C, this compressibility. Is it an oil well or a gas well? If it's an oil well, oil is a liquid, it has a very low compressibility. The hydraulic diffusivity is much higher with low compressibility systems. It's sort of like the same reason why sound travels faster in a liquid than a gas. Okay? Same sort of concept, not exactly the same, but similar. So the compressibility of liquid is much lower, and therefore that's on the denominator, so the hydraulic diffusivity will be higher. Other things that come into it are porosity. If the porosity is very high, the hydraulic diffusivity will be lower. Okay? So there's lots of different things that come into this. What doesn't come into this, and what may be surprising to some people, is that there's no mention of flow rate in here. Okay? I think it seems intuitive that if I flow a well at a very high production rate, let's say 10,000 barrels per day, that I should be able to investigate the reservoir faster. Well, it turns out that that's not the case. The production rate is sort of like if we can think of, and this is a little bit of an approximation, a pressure transient isn't really an impulse, but I'm going to think of it as an impulse. Think of this as an impulse or a pulse that travels through the reservoir. Okay? That's one way to think about this. The production rate, the speed with which this pulse moves through the reservoir is really a function of the hydraulic diffusivity. The amplitude of the pulse is a function of the flow rate. Okay? So we need to have a flow rate there in order to measure that pulse. If the flow rate's too small, in theory, this flow rate could be 1 drop of oil per day. And we'd still be able to get the pressure transient to move through the reservoir. But we wouldn't be able to measure anything because the amplitude's not big enough. So if we want to have a pressure transient that we can actually read and get some information out of, we need to have enough of a production rate there that we can actually read it. So the amplitude of that signal is analogous to the production rate, and the hydraulic diffusivity is analogous to the speed of the pressure transient through the reservoir. And that's really how we describe the radius or region of investigation. The transient equation, we're going to show this. I'm not going to derive this transient equation, but we're going to just talk about it. If we want to see the full derivation and the full exploration of the transient equation, that would be covered in a pressure transient analysis course. You could spend a whole day just talking about that. For the purposes of this course, we really just want to look at the transient equation and see how it impacts what we're doing. So this equation describes, for example, radial flow in an infinite acting reservoir. That would be our case like this. This is our well, and it's draining effectively a large area. So radial flow is the flow lines coming into the well this way. And this equation is the theoretical equation that describes that. So it's similar in a lot of ways to, if we go back and look at this, to one of these equations, right? These are the equations for boundary-dominated flow. But it's different because the boundary-dominated flow equations are the long-term, late-time equations. The transient equation that I'm going to show you is the early-time equation. So this is the equation that applies very near the beginning of production and may stretch out longer depending on how low the permeability is. If you'll notice, we've formed it in the same format with the same variable on the left-hand side as the other equations. We're interested in the normalized rate. We want to be able to plot all these things on the same graph. So we're interested in the normalized rate. And then there's a bunch of stuff on the right-hand side. We don't want to get into the details, but what it's a function of is things like permeability. There's skin in there, and there's some other things. But really, permeability and skin are the main things that are going to come out of the transient equation once we analyze the data. So we've, at the end here, we can plot all of these curves together. The blue and the purple, or the blue and the pink curves, again, these are the boundary-dominated flow equations for constant rate and constant pressure. The red curve that I've shown on top here is the transient flow equation. Okay? And I've made the comment here, this compares to an ARPS superhyperbolic, and the superhyperbolic means that, in fact, the transient equation, when you end up looking at it and comparing it to the standard ARPS decline equations, looks a little bit like a hyperbolic with a b value that's greater than 1. And what that b value is, we're not sure, but it's a large b value. Okay? In other words, this transient equation has a very distinct shape. It's almost got like an L shape to it. It drops very quickly and flattens out. Whereas the boundary-dominated equations decline much more slowly. Okay, so these are the equations or the curves that we now have. Now we got to figure out how to use them. Okay, so how do we put all these things together to use them properly? And we're going to get to that in just a minute.